The great debate about the structure of the universe took place 100 years ago in 1920. Debate is a formal discussion on a particular topic in a public meeting or assembly in which opposing arguments are put forward. Formal debates often have a moderator and an audience in addition to the debate participants. Logical consistency, factual accuracy, and emotional appeal to the audience are all elements of debate. For formal debates, there are a framework of rules for determining the winner of the debate. Galileo, the father of modern astronomy, presented his heliocentric solar system model in his 1632 work, Dialogue Concerning the Two Chief World Systems. His work was a debate formatted as a series of discussions taking place over 4 days between two philosophers and a layman. His debate involves rebuttals of the objections raised by traditional philosophers towards Copernicus's heliocentric system, observations that were incompatible with Ptolemaic model, including Galileo's observations of the phases of Venus and the movement of sunspots, arguments refuting other aspects of the elegant unified theory of heavens around a fixed Earth, which also required that the moon be a perfect sphere, yet Galileo found large mountains on the moon, and that orbits do not cross, yet Galileo found moons around Jupiter. Direct physical argument that the Earth's motion around the sun causes tides was the fourth part of debate that Galileo presented. The three players are Salviati, who argues for a Copernican heliocentric model using evidence provided by Galileo's viewpoint and his observations. He was named after one of Galileo's friends and is considered the academic of the trio. Segreto is initially neutral and provides intelligent arguments. He is also named for one of Galileo's friends. Simplicio, on the other hand, presents dogmatic arguments that support the traditional views of a geocentric model, refuting Copernicus on ridiculous terms that were common of the day. Although Galileo's observations were straightforwardly a refutation of the geocentric model, specifically those of the phases of Venus and other ones being the sunspot cycles, Galileo's argument about tides are incorrect. Tides are mostly caused by gravitational attraction of the Earth to the moon and the moon's orbit. And while the names Salviati and Segreto evoke respect, the fact that Simplicio used arguments made by classic Greek philosophers and the Pope was interpreted as making fun of the Pope, making him sound like a simpleton. It was a double entendre and comically stupid. So censors thought it insulted the Pope, and on this basis Galileo was convicted of heresy and placed under house arrest. The idea of debate, however, caught on. And while sound arguments of verifiable evidence explained through logical reasoning are acceptable, there's always this gray area in debate about the acceptability of emotional appeal, particularly where attacks of opponents become personal or ad hominem fallacies. In 1979, the Catholic Church re-examined Galileo's case and found that Galileo should not have been condemned. And in 1992, Pope John Paul II endorsed those findings. Generally, such misery can be avoided by having clearly written rules of debate formed over before the show and having a moderator who remains neutral and ensures fair play. There's some events that led to the Great Debate. First, Kepler showed that the orbit of planets and comets could be fit as ellipses with the sun at one focus. Kepler also showed that the apparent brightness of objects varies inversely with the square of the distance to the object. Edmund Halley determined the orbit of a comet, now known as Halley's Comet, and predicted its appearance in 1758. This sparked worldwide interest in being the first to discover it in the night sky, and among those was young astronomer Charles Messier, who became obsessed with finding comets. Messier created a catalog of not comet objects, objects that were diffuse and could fool comet hunters. Here's Messier's comet fooling catalog. These are diffuse objects, globular clusters, and nebulas and galaxies as we know them today. There was growing interest in catalogs of nebulae. What is the nature of the universe? Are there gas clouds in the Milky Way, or are there island universes? Another key event was the discovery of Henrietta Swan-Leavitt of the period luminosity relationship of Cepheid variables. She is an American astronomer who revolutionized astronomy with this discovery. After graduating from Radcliffe College, she traveled in America and in Europe, during which time she lost her hearing. She had financial support from her family, and although deaf, she volunteered as a research assistant at Harvard College Observatory under the astronomer Edward Pickering, who had initiated a research program on the measurement of stellar magnitudes. 7 years later, in 1902, Pickering hired Leavitt to the observatory's permanent staff at 30 cents an hour. Leavitt worked there until her death and received little recognition for her contributions during her lifetime. In the early 1900s, women were not allowed to operate telescopes, and Pickering did not want women to work on theoretical studies. Instead, the ladies measured and cataloged the brightnesses of stars as they appeared in the observatory's photographic plate collection, sometimes called Pickering's harem. These ladies were regarded as human computers. Leavitt was eventually given the task to study variable stars. Henrietta Leavitt studied the variable stars and noticed patterns in the light curves. Some had distinct periodicity. She measured the period. The period and magnitude of variation of a few Cepheid variables are discussed in the online article titled "The Top 12 Naked Eye Variable Stars," written by John Iles, published in Sky and Telescope in March of 2010. Since the luminosity, that is, absolute brightness of stars, could be determined from their period, and since the apparent brightness could be measured, the distance to these stars could be determined using Kepler's inverse square formula. Leavitt measured thousands of variable stars in the images of the Magellanic Clouds. These are small irregular galaxies in the local group of the Milky Way galaxy and are seen in the southern hemisphere. In 1908, she published her results in the Annals of the Astronomical Observatory of Harvard College, noting a pattern. Brighter stars appeared to have longer periods. In 1912, she concluded that the Cepheid variables with greater intrinsic luminosity did have longer periods, and that the relationship was quite close and predictable. Leavitt used the simplifying assumption that all the Cepheids within each Magellanic Cloud were approximately the same distances from Earth, so that their luminosity could be deduced from their apparent brightness. She wrote that of her discovery, a straight line can be readily drawn among each of the two series of points corresponding to the maxima and minima, thus showing that there is a simple relation between brightness of the variables and their periods. Her discovery and mathematical modeling enabled astronomers to measure the distance to these variable sources. In the 1920s, astronomers identified faint fuzzy objects called nebulae in their telescopic observations. The interest in understanding where and what these objects were sparked the Great Debate. From 1902 to 1920, Curtis worked at Lick Observatory in Santiago, Chile, surveying nebulae. In 1912, he was elected president of the Astronomical Society of the Pacific. He investigated the then called spiral nebulae and became convinced that they were independent star systems. In 1917, he argued that the observed brightness of novae found by him and George Ritchie on photographs of spiral nebula indicated that the nebulae lay well beyond our galaxy. He also maintained that extremely bright novae, later identified as supernovae, could not be included with the novae as distance indicators. During the war years, 1917 to 1918, Curtis organized and conducted a navigation school for the United States Shipping Board in San Diego, California, in teaching navigation in the Naval Officers School in Berkeley, and as a research physicist in the optical section of the National Bureau of Standards in Washington, D.C., where for a time he was acting head of the optical section. In 1918, Curtis measured Messier Object 87 and was the first to notice the polar jet, which he described as a curious straight ray apparently connected with the nucleus by a thin line of matter. In 1920, he was appointed director of the Allegheny Observatory. From his work surveying nebulas, Curtis advocated the now accepted view that other galaxies apart from the Milky Way existed. He estimated that the Andromeda Galaxy, then known as the Andromeda Nebula, to be 500,000 light years away. People, including Harlow Shapley, opposed this view. From 1914 to 1921, Harlow Shapley was at Mount Wilson Observatory, where he calibrated Henrietta Swan-Leavitt's period luminosity relationship for Cepheid variable stars and used it to determine the distances to large groups of stars called globular clusters. At that time, very little was known about the overall shape of our galaxy or our place in it, though it was presumed that the solar system was at the center. By the time he finished his research in 1919, after publishing more than 40 research papers, the overall shape of our galaxy was coming into focus, including the position of our own solar system. Shapley proposed that the Milky Way galaxy was 300,000 light years in diameter, far larger than previously assumed, and that the spiral nebula lay within it. The great debate given at the National Academy of Sciences on 26 April 1920 is one of the most dramatic episodes of the history of astronomy. There were oral arguments given by Curtis and Shapley, followed by extensive publications. Although Shapley's central argument was that the universe was much larger than previously thought, the debate is generally viewed as centering on whether the spiral nebulas were island universes. More specifically, Curtis argued that the Sun is at the center of a relatively small Milky Way galaxy because the star count analysis and distances estimates from the spectral types and intrinsic brightnesses of stars suggested a smaller heliocentric galaxy. He did not believe that Cepheid variables were good distance indicators. Spiral nebulae are galaxies beyond our own because novae in Milky Way, similar to novae in spiral nebulae, implying a very great distance. He thought that Slipher's spectroscopic measurements of high recessional speeds for nebulae implied they were not galactic arguments, which would be moving much more slowly relative to the Sun. He thought that the apparent sizes of spiral nebulae consistent with his estimate for the Milky Way when spiral nebulae placed at actual galactic distances, and that photographs revealed absorbing material in nebulae consistent with that he thought present at galaxy's edge. He did not believe von Mahn's measurements. More specifically, Shapley argued that our Sun is far from the center of the galaxy because globular clusters more concentrated toward one half of the sky than the other half of the sky. Variable star distances implied globular clusters were concentrated on one half, and therefore the Milky Way must be very large because variable star distances implied the galaxy was much larger than previously supposed. This meant that the spiral nebulae, now known as galaxies, are within our galaxies because of the great extent of the galaxy precluded by spirals from being other galaxies. He further argued that von Mahn's proper motions implied spiral rotation speeds close to the speed of light. That is, distances to nebula must be small for the implied rotation to be physically acceptable. In summary, Shapley's research at Mount Wilson Observatory convinced him to argue that the universe is one gigantic galaxy that is 100,000 parsecs across. The Sun and the solar system are far from the center of the galaxy. Nebulas are huge clouds of gas and dust and are actually part of the Milky Way galaxy. In summary, Curtis's research at Allegheny Observatory led him to argue that the universe is made up of many galaxies, that our galaxy is smaller than Shapley suggests. It is 10,000 parsecs across, and that the spiral nebulae and other very distant galaxies are completely separate from the Milky Way. In summary, Shapley believed that the diameter of the Milky Way galaxy was 300,000 light years, and that the Sun was not the galaxy's center, but 60,000 light years away, and that the Milky Way was so large it was the entire universe. He believed that the spiral nebulae were gaseous clouds repelled by the Milky Way's light pressure. Curtis believed that the diameter of our galaxy was 30,000 light years, and that the sun was very close to or at the center of the galaxy, and that the spiral nebulae were galaxies. That is, the spiral nebulae were island universes in their own right. The Great Debate set the stage for the work of Edwin Hubble, who discovered the expansion of the universe. Edwin Hubble, founder of observational cosmology, resolved the debate. His observations of Cepheid variable stars in the Andromeda galaxy showed that both were correct to some extent. Curtis was right about the spiral nebulae being very far away and being galaxies separate from the Milky Way galaxy. And Shapley was right that the solar system is far from the center of the Milky Way galaxy. Shapley was correct that the sun is located off-center of the galaxy. Shapley was correct that the galaxy is much bigger than previously thought, although he overestimated the size. And Shapley was correct that the Cepheid variables are good distance indicators. Curtis was correct that the spiral nebulae are external galaxies. Curtis was correct that von Maunen's results were not good, and both Curtis and Shapley were incorrect that the interstellar absorption of starlight by dust was unimportant. In 1925, Curtis invented a type of film plate comparator allowing two plates, each 8 by 10 inches, to be compared using a set of prisms and placing other plates stacked along stages rather than next to one another, as was the norm, thus allowing the body of the device to be measured just 60 by 51 centimeters. In 1930, he accepted the directorship of the astronomical observatories of the University of Michigan. Although Professor Curtis came to Michigan prepared to design a large reflecting telescope in Ann Arbor, unfortunately, by the time he completed the design of the telescope, the funds were no longer available for its construction due to the Great Depression. During his lifetime, Curtis participated in 11 expeditions of the study of solar eclipses. His contributions to this impressive number are underscored by a quote from a fellow astronomer, Campbell, at the 1900 eclipse. Campbell said, "We do not see how we could have dispensed with his services, nor how anyone could have met with the exacting demands better than he did." After the debate, Shapley was hired to replace the recently deceased Edwin Charles Pickering as director of the Harvard College Observatory. He hired Cecilia Payne, who in 1925 became the first person to earn a doctorate at Radcliffe College in the field of astronomy for work done at Harvard College Observatory. In his latter years, he became a political activist during the latter New Deal and Fair Deal. He was on the original standing committee for the Foundation of Study of Cycles, on the Board of Trustees for Science Service, now known as the Society for Science and the Public, and helped found the government-funded scientific associations, including the National Science Foundation, and he put the S in UNESCO, the United Nations Educational, Scientific, and Cultural Organization. Sparking controversy, Shapley was subpoenaed by the House of Un-American Activities Committee for his role as a member of the Independent Committee of Arts, Sciences, and Professions, major political arm of the Russophile left, for opposing the United States Representative Joseph William Martin Jr. during midterm elections that year. In 1947, he became president of the American Association for the Advancement of Science. More controversy was sparked by his inaugural address, during which he referred to the global threat of the quote, genius maniac and proposed the elimination of quote, all primates that show any evidence of signs of genius or even talent, among the other threats that included drugs that were suppressed for the desire of sex, boredom, world war with weapons of mass destruction, and plague epidemic. So he got kind of politically involved and very satirical in his commentary. Never leaving his scientific work, in 1953 he proposed the liquid water belt theory, now known as the concept of a habitable zone. And we'll discuss that when we discuss life in the universe. One of his sons, Lloyd Shapley, is a mathematician and economist. Lloyd Shapley won a Nobel Prize in Economics in 2012. The galaxy's size and shape as we know it today is pretty close to that described in the lyrics of the Galaxy song composed by Eric Idle for Monty Python's movie, The Meaning of Life. Here are the lyrics. Our galaxy itself contains 100 billion stars. It's 100,000 light years side to side. It bulges in the middle, 16,000 light years thick, but out by us, it's just 3,000 light years wide. With 30,000 light years from galactic center point, we go round every 200 million years. And our galaxy is only one of millions of billions in this amazing and expanding universe. There are several recent debates in astronomy. In 1995, the distance scale to gamma ray bursts was debated. In 1996, the scale of the universe was debated. And in 1998, the nature of the universe was debated. The 2020 debate question is, how will humanity first discover extraterrestrial life? About 30 astrophysicists, planetary scientists, and astrobiologists have given video recordings of their answer to this debate question, and the links are available at the Astronomical Picture of the Day site run by NASA. Go apod.nasa.gov/debate/debate100.html.